let's just jump right into it. Look, if you've ever stared at a calculus textbook and thought it was just this terrifying wall of random, disconnected formulas, I completely get it. Honestly, I don't blame you. But today, we're going to flip the script. We are going to discover together that calculus is actually this beautiful, incredibly logical engine. We're starting from absolute zero, literally just basic shapes, and we're going to build this machine piece by piece. Let's see how it all clicks together.
You know, there's this great saying that calculus isn't a collection of unrelated formulas, it's a story about change. And honestly, that perfectly sets up our goal for today's explainer. We're going to build a math machine, gear by gear, to understand exactly how things move in our universe. We are absolutely not going to blindly memorize things today. We are going to build.
So, here is our blueprint. We'll lay out the basic design of our machine, take a quick detour into the land of triangles, and then get into the real engine: derivatives, connecting the rules, curvature, and finally, integration. It's going to be a really fun ride.
All right, let's look at the foundational blueprint of this machine we're building.
To keep things super simple, imagine a little toy car just rolling across the floor. Our entire mathematical machine is built to answer just 4 basic questions about its journey. Step 1, where is the car right now? In math terms, that's our function. Step 2, how fast is its position changing? That's the first derivative. Step 3, is that speed itself increasing or decreasing? Like, are we hitting the gas or slamming the brake? That is the second derivative. And step 4, if I only know how fast the car was going, can I somehow run the movie backward to figure out where it started? That's integration. So, quick practice to lock this in. If I simply ask you, where is the car located? Which mathematical tool are we grabbing? Right, the function.
But before we get the car fully moving, we have to make a quick stop in the land of triangles.
So here we have sine, cosine, and tangent. And please, do not think of these as scary random letters. Think of them as 3 different windows looking at the exact same angle. That classic memory trick, SOHCAHTOA, it just tells us which sides of a right triangle we're comparing. Like, if you have a triangle with sides measuring 3, 4, and 5, the sine of the angle is just 3 over 5. The cosine is 4 over 5, and the tangent is 3 over 4. It's just 3 views of one single angle. And thanks to the good old Pythagorean theorem, a squared plus b squared equals c squared, we get this ultimate master key. Sine squared x plus cosine squared x equals 1. From that one simple truth, literally all the other reciprocal and quotient rules are naturally born.
And this perfectly shows how math just builds on itself. People get so intimidated by the double angle formula, but look at this comparison. It isn't magic. The formula for sine of 2x is literally just the normal addition formula, sine of u plus v, but you just use it by adding x to x. It's the exact same tool, just used creatively. So, quick practice. If we make our angle 45 degrees, the sine of 90 degrees just becomes 2 times the sine of 45 times the cosine of 45, which beautifully crunches down to exactly 1.
Okay, now it's time to fire up the engine. Let's talk about derivatives and changing speeds.
Now, if you open any calculus textbook, you're probably going to get hit with a terrifying wall of like 36 basic differentiation rules. Listen to me, do not panic. What you're seeing is just a diagram of the entire machine all at once. We're going to triage this. We're going to ignore almost all of it for now, because honestly, you don't need to memorize a giant parts list just to drive a car. The truth is, you really only need to master these 10 fundamental rules first. Just these 10 core gears. Once these feel natural to you, the rest of that massive, scary chart becomes totally harmless, because you'll actually understand the underlying logic of the engine.
Let's start with the most important concept of all. In plain English, the first derivative simply asks, if I change the input just a tiny, microscopic bit, how much does the output change? It's exactly like glancing at your speedometer at one exact split second in time. Geometrically speaking, it's the slope of the tangent line that's just barely grazing our curve. It's the pure measure of instantaneous change.
And that brings us to the absolute king of basic differentiation, the power rule. It is incredibly simple. Step 1, bring the power down to the front. Step 2, reduce the power by 1. That's it. Let's do 3 quick examples. X squared, that becomes 2x. X cubed becomes 3x squared. X to the 7th becomes 7x to the 6th. You see the rhythm? So, practice question for you. What do you think x to the 10th becomes? Yep, bring down the 10, drop the power to 9, and you get 10x to the 9th. Boom, you're doing calculus.
Now let's start connecting these rules together, just like gears in a transmission.
So, we use the product rule when 2 changing things are being multiplied together.
Think about a rectangle where both the length and the width are growing at the same time. The logic is simple. The first part stays the same while the second changes, plus the second part stays the same while the first changes. Let's hit 3 quick examples. First, x squared times sine x becomes x squared times cosine x plus 2x times sine x. Second, x cubed times e to the x becomes x cubed times e to the x plus 3x squared times e to the x. Third, x times the natural log of x becomes x times 1 over x plus 1 times natural log of x. Easy. Now the quotient rule is for division, and it has a similar rhythm. Bottom times the top's change, minus the top times the bottom's change, all over the bottom squared. Let's do 3 fast ones here too. Sine x over x becomes x times cosine x minus 1 times sine x all over x squared. E to the x over x cubed becomes x cubed times e to the x minus 3x squared times e to the x over x to the 6th. And 1 over x becomes x times 0 minus 1 times 1 over x squared. Just gears turning gears.
Then we have the chain rule, which is absolutely essential. This is for when you have a formula trapped inside another formula. It's exactly like a Russian nesting doll. You handle the outside doll first and then multiply by the inside doll's change. 3 examples. Number 1, if we have sine of 4x, the outside machine is sine, which changes to cosine. The inside machine is 4x, which changes to 4. Multiply them and you get 4 times cosine of 4x. Number 2, e to the power of 3x becomes e to the 3x times 3. Number 3, sine of x squared becomes cosine of x squared times 2x. Always outside first, inside second.
Look how beautifully simple the rules for exponentials, logarithms, and basic trig become once you understand these core gears. Like the derivative of e to the power of x, it's incredibly special. It is its own derivative. The natural log of x just cleanly becomes 1 over x. And since we already visited the land of triangles, we know the derivative of sine is simply cosine. Let's do a rapid-fire practice round. What is the derivative of e to the 5x? It's e to the 5x times 5. What about the natural log of 2x? 1 over 2x times 2. And cosine of 3x? That's negative sine of 3x times 3. You've got this.
All right, let's level up. It's time to talk about curvature and turning points.
Now we're going to push our little toy car to the limits by asking a totally new question. We know our speed, but is the steepness itself increasing or decreasing? Like we said earlier, if the first derivative is your speed, the second derivative tells you if your foot is on the gas pedal or the brake. It tells us about the bend or the curvature of our graph. Let's take the equation y equals x cubed. The first derivative, our slope, is 3x squared. The second derivative, our curvature, is 6x. This tells us exactly how the slope is shifting at any given point.
And this is exactly how we find the peaks and valleys of literally any system. First, we set our first derivative to 0. That finds the flat, horizontal spots, the stationary points. Then we check the second derivative to see our shape. If the second derivative is negative, the graph is bending downwards like a hill, so we have a maximum. If it's positive, it's bending upwards like a valley, so it's a minimum. Let's do a quick practice. Take y equals x squared. The first derivative is 2x. At x equals 0, the slope is 0. But the second derivative is a constant, positive 2. Positive means it bends upward, which means x equals 0 is our valley, our minimum.
Finally, we reach integration and the big picture. It is time to put our machine in reverse. We've spent this entire time breaking things down into their rates of change. Now we build them back up. Differentiation is breaking the change down. Integration is the sort of magical process of rebuilding the original quantity. If I only have the speedometer data, integration lets me reconstruct the car's entire path. It's literally like running a movie backward through time to see exactly where our car started.
And the rule for this is the exact logical opposite of the power rule we learned earlier. The power integration rule has 3 steps. Step 1, add 1 to the power. Step 2, divide by that new power. Step 3, add plus c. We absolutely have to add that c, which stands for constant. Why? Because when we run the machine backward, we have no idea if there was just some plain, unchanging number sitting there that got erased to 0 when we differentiated it. Try reversing 2x right now in your head. Add 1 to the power of 1, making it 2. Divide 2x squared by 2, which leaves just x squared. Add c. Boom. Our original function was x squared plus c.
I mean, just look at this magnificent hierarchy we just built together from scratch. 1. Triangles, setting up our basic geometry. 2. Functions, handling our inputs and outputs. 3. The derivative, measuring pure change. 4. Tangent lines, giving us that instantaneous slope. 5. The second derivative, revealing the hidden curvature. 6. Maxima and minima, finding the peaks and valleys. And 7. Integration, magically reversing the whole process.
So from now on, whenever you look at calculus, I want you to make me a promise. Don't ask how to memorize a giant list of equations. Instead, ask yourself, what is the object and what is the machine asking me to do? View every formula as just a single handy tool inside this beautiful logical engine we just built. You now hold the blueprint to the mechanics of the universe. So, what are you going to build with this machine next?